anything later on, so please do stop around for that. But now we're moving into another part of the day, and we're going to hear more from Reactor technology companies, which is great, and I think there's some real life examples here as well of some of the things we've been talking about around industrial decarbonisation, so looking forward to hearing that. So to open the session, we've got Steve Coates here from X Energy. Over to you, Steve. Look forward to hearing your presentation. Thanks, Phil.
Good morning. As Phil said, I'm Steve Coates from X Energy. A little bit about my background. I started my career in the operational side of the nuclear business in the UK and abroad, so Hartlepool Power Station, Dungeness Power Station, and then in the last 5 years out in Abu Dhabi on a new build project in Reactor. Joined X Energy in January of this year, so enjoying my time in X Energy. I'm pleased to be here to give you an update or introduce you to it. A little bit about X Energy, but more about securing delivering advanced nuclear projects. I guess when you go through this, there's nothing in here that's rocket science on you, really. We know what the components are of securing and delivering advanced nuclear projects, but there's a few key messages I'd like to get across of advanced modular reactor technology, in particular X Energy technology, and how we support the energy security ambitions in the UK, and two, decarbonisation in the UK in the future and moving forward. So one component you need, or the first component you need, is a good organisation. So we're an organisation that's been around since 2009, based out of Rockville, Maryland, in the United States. We've got over 550 full-time employees on the project, supported by around about 1,000 consultant contractors, engineers, scientists, designers, business development, the whole gambit of what you need to bring a project to market. And obviously you need some money. We've been awarded in the US $1.2 billion of federal funding through the Advanced Reactor Demonstration Program. So we've got the organisation, we've got some money. In the UK, we partner with Cavendish Nuclear, part of the Babcock International Group. You obviously see their footprint is wide, or right around the UK, in every civil and MOD facility in the UK in some way, shape or form. They've been around a long time. They've got a deep and broad supply chain. They understand the nuclear safety culture of working on operational and decommissioned sites and military sites. So we feel they're a good fit for X Energy in the UK in terms of deployability. So Cavendish form part of that, the position where we are in the UK in terms of our deployment. So that's our organisation, US, UK in a nutshell. This is the key slide, really. I don't know, for those of you who were in the room earlier, when I asked the question regarding demonstrator reactors and R&D reactors by mid-2030s in the UK. So X Energy have got signed a contract with Dow Chemicals in Texas. And you can see the site there. It's on the Gulf Coast. It's called Seadrift, and it's Dow Chemicals plastic manufacturing facility. And Dow Chemicals have gone into business, I've gone with X Energy to build a 4-pack. So we're building 4 reactors on the Dow Chemicals site. And the reactors are 200 megawatts thermal, 80 megawatts electrical release, so that's 320 megawatts electrical in total. And they're going to use that for 2 reasons. They're going to use it for electrical supply, direct electrical supply to the site, and steam for decarbonisation and their process use. And there is a facility to tie into the grid in the States for surplus electricity. So the point being there that from an X Energy perspective, we're not in the place of R&D and development. We are a demonstrator, we are deployable, and we're deployable already there with 4-pack. And we're on site in Dow Chemicals in Texas today doing site characterization work. So another component is how mature your technology is. High temperature gas reactor, which is ours, has been around a long, long time, right back to, you can see there on the bottom left, right back to the UK in the 1960s and 70s in Winfred and the Dragon Reactor. I'm not going to step through each of them there, but it just gives a flavour of how long high temperature gas reactors have been around. So they're mature, they're well developed, and they've been in operation in many countries around the world. So with all of that, with the organisation, with the fact that we're actually deploying in the US with a mature technology, what makes us different? Well, the first thing that makes us different, one thing that we're proud of, is the fuel we use. And it's an intrinsically safe fuel. It's 6 centimetres in diameter, about the size of a snooker ball. It's triso fuel particles, about 1 millimetre in diameter, surrounded in graphite layers, and they are intrinsically safe. And when they're formed as a pebble, we call them pebbles, when they're formed as a pebble, they are intrinsically safe and have been tested to 1600 degrees Celsius, and they don't melt, they don't break. So that what that means is the containment is within the fuel. So we don't have the big containment buildings that you see in the light water reactors around the UK and advanced gas cooled reactors in the UK, which brings costs down. The low power reactor density and the self-regulating core, it shuts down, so if you lose cooling, it shuts down, maintains subcritical conditions, and the temperature profile does spike, but then cools back down again. So that intrinsically safe fuel and the passive safety systems make for a safe reactor and a fuel that we describe as one of the safest fuels on the planet. And then our technology, in each of the reactors on the nuclear island, there are around 200,000 pebbles in each reactor. And as I said earlier, we sell them in individual reactors of 200 megawatts thermal, 80 megawatts electrical. However, for scalability and cost effectiveness, we recommend that you buy them in packs of 4 if you're interested. And that's 200 megawatts. So that would give you 320 megawatts electrical, 800 megawatts thermal power. Just as a side of that, we are, and this gives it, I know the other two guys are going to present after me. I'll talk similar stuff in terms of the agility and flexibility of the MR community, I'll call it, the SMR community. So, example, we have got ongoing discussions in Washington State with Energy Northwest to build a 12-pack. And the 12-pack will be for electricity. They want flexible electricity. One of the things that the XE100 can do, it can load for. So Dow Chemicals are taking steam and electricity. Energy Northwest want to take electricity for flexible use purposes. So the reactor, 200,000 pebbles in a reactor core, and they cycle through. Each pebble goes through 6 times in its life, and that's over a 3-year period. And once they're spent, they're put in the fuel casks and stored on site. And obviously the heat is then transferred from the reactor core across the steam generator, where you produce the steam to either 1, drive the turbine, produce electricity, or 2, take the steam take the steam for process end use. And I'll come on to that in a slide or two's time. So, organisation, ability to build a fuel that is intrinsically safe, and a reactor technology that is well developed and mature, all coupled together to give you this end product of electricity or off-take steam. And the off-take steam, you see that can be used for a number of reasons. Conventional power generation, we talked about. Something that we're looking into in the UK in particular, synthetic fuels production, hydrogen production, district heating, data centres. Probably less so in the UK at the moment, but there's a lot of interest in the United States about data centre, supporting data centre powers, especially with artificial intelligence and the way that's moving, and desalination and high temperature steam for industrial use. So that's X-energy in a more international sense, I'll call it. What do we want in the UK? Well, our fleet deployment in the UK is 40 reactors, that's 3.2 gigawatts. We firmly believe that we support the energy security policy from the British government. Certainly support the decarbonisation efforts of the UK government through the steam offtake and clean electricity. We're competitive with other technologies, certainly. And in terms of deployability, if we deploy today in the UK, our first reactor will be in commercial operation in early 2030s, 2029, 2030. We're going to bring £20 million worth of value to the UK economy, and a full pack with cost in the range of £1.5 to £2 billion for a 4-reactor pack. High UK content, and I'll come on to that in a couple of slides' time, but the high UK content, with our ambition is to get an 8% UK supply chain. So if I go back to the fuel is a good example. At the moment, we're building a fuel fabrication facility in the US. And when we're successful in the UK, our first fuel load for the first reactor will be from the US. But that's not our intention, our ambition in the longer term. The long term is the fuel will be built in the UK. So we are talking about fuel fabrication facilities in the UK, UK fuel for UK reactors. So that's one element of it. We've signed memorandums of understanding with a number of suppliers in the UK. Howden's being one for the helium reactor, helium circulators. Sheffield Forge Masters for the exploring what the art of possible is with respect to RPVs and other components for the reactor island. So we're moving into the supply chain, and it's our ambition to get to an 8%. Now that 8% UK supply chain, I'll speak open and honestly, it won't be from day one, it's a work towards, it's got to be. We all know what the challenges are on the UK supply chain and where we are, but it is our ambition to get to a high UK content. So we have 40 reactors that are the UK, ex-Energy UK ambition, that's our business model, 40 reactors. The first 12 reactors, we're looking to build in Hartlepool. On the site, the current Hartlepool nuclear site, the site is not on the station there. That's the existing site that we're looking to build on the left, on the back of that, behind the visitor centre and the training centre, and that's a 12-pack. Oh, why have we picked Hartlepool as a site? Well, a number of reasons really. Firstly, Hartlepool existing site is still in operation and will be operation until 2026 and maybe beyond that. So they've got a lot of knowledge and experience in high temperature gas reactor operations, maintenance, engineering, everything that we're looking for. So there's a natural fit for a high temperature gas reactor to be sited at Hartlepool. So we picked it for that reason, in terms of the knowledge and experience they've got. But there's another piece as well, which is probably closer to my heart as an ex-operator, is there's 40 years of nuclear safety culture built in the Hartlepool site. And anybody who's been on an operational site or been involved in nuclear safety culture, to build a nuclear safety culture from the ground up takes a long, long time. And they've got 40 years of experience on that. So not only have they got the knowledge and experience of operating, maintaining, and safely running a reactor, a high temperature reactor, they've got the culture, the nuclear safety culture sitting behind that as well. And that's something we want to tap into. The second piece for Hartlepool, where we differentiate ourselves a little bit, is you can see around there the different clusters of industries. You're building chemical works, Tees Port, Teesside Steel Works, Wilton International, and Tees Works. The next slide sort of shows that the amount of business that is in the Tees Valley, that the Tees Valley Combined Authority have set a target to be net zero by 2040. A lot, if not all, of them industries will need some assistance in achieving their decarbonisation ambitions, and we believe we can support that through clean electricity and steam offtake, whether that's for process use, hydrogen production, synthetic fuels, district heating, everything I'm talking about previously. So we sit in the centre, not quite the centre of it, but successful deployment of Hartlepool will give us access to all of them industries who have got a target of net zero by 2040. So, fantastic opportunity for us to support the community, the local community in Hartlepool with high quality jobs, ongoing high quality jobs, high paid jobs, and support fill the energy gap, go somewhere filling the energy gap and energy security, and decarbonisation efforts. So that's why we picked Hartlepool, and that's a big component for us at our first site. We are in discussions with EDF and others around the Hartlepool site. EDF can maintain a technology agnostic position, and I understand that, until GBN announced the technologies and the signing arrangements. Well, that doesn't mean we don't talk to EDF. We talk to them regularly, and we have a very strong relationship with EDF. However, they maintain an agnostic position. So that's the biggest component for the UK for us is for Hartlepool site, the culture, the skill set, the ability to support decarbonisation efforts, and direct wire or national grid connections for electricity. Benefits to suppliers, I'm not going to go through this, it's pretty obvious, you know, anybody who's been involved in construction, pumps, valves, concrete pouring. I was on Hinkley Point C yesterday, a tour around Hinkley Point C yesterday, and that brings it to, you realise what it's like to build a nuclear power plant when you go on Hinkley Point C, how much concrete's being poured. So it was quite exciting to go around Hinkley Point. I think that in a few years' time, we could be doing that in the UK. We could be pouring concrete, fitting valves, pumps, generators, and supporting the energy security of the United Kingdom. So we talked about 80% supply chain. So I'm not going to go into the detail of what we're looking for, but it's pretty obvious there. Some of the success factors for us in particular, we want our first site secured, Hartlepool, and that will give us a path to fleet employment. We need confirmation of a project delivery model into GDA, everything that was talked about in the first session. There's a place for deploying AMRs in the nuclear roadmap and facilitating progress on the above. And the key thing is, I guess all the vendors, technology vendors in the room tend to agree, I think we want to move at pace to capitalise on synergies with the existing fleet. I think every technology vendor, X-Energy, are aligned with that. Let's move at pace and let's start building these things, because we've got a place to do it, and this is the time to do it. And Phil, I think I'll stop there.
Thank you very much, Steve. Very exciting to hear the plans there and the need to provide those industries with the energy, because I think one of the key things that as an energy provider we need to offer the industries is the ability to produce green products. And if those companies that are producing products today with higher carbon electricity can't access low carbon in the future, then they themselves will struggle to compete. So great to see. Right, now we're going to move on to Michael Crawford, who I'm delighted to introduce. He's going to talk to us about Rolls-Royce technology and the role of AI as part of that.
Thanks very much, Phil. So yeah, today I'm not going to speak too much about the Rolls-Royce SMR and the design, because quite frankly I'm sick of talking about it, and I'm sure everybody is sick of hearing about it. So this presentation is all about how the world of data and AI and nuclear are on a bit of a collision course, certainly in my opinion. So I'll take you through some thinking. Rule one of sort of winning over an audience, start with a giant wall of text. I'll try and make it more interesting as it goes on, but just to set the background, the context of the data industry, you know, it's a big data energy hungry industry. So worldwide, it accounts for about 1% of all energy use. But in the US, it's around 2%, that's an advanced economy. This is 2020 numbers, so that number is growing rapidly, sort of 20% a year before we take into account AI and the effect that could have. That could radically transform those numbers, and the projections that we're seeing from conversations with people in the industry, big data users, it's eye-watering numbers are heading our way. And all of that growing demand is new. That is demand that is not there today, it's not met by existing generation. we're struggling to meet, the daily needs today, let alone the growth as we go to EVs and heating and all that. How are we going to cope with gigawatts and gigawatts of new demand to support AI? The profile of that demand and why it's really good nuclear is because it's 24/7, they have the 5 nines reliability, which means always on, and they have to absolutely guarantee that as the service they're providing to their clients and their customers. So you can already see the synergies here with nuclear. It's brand new, enough to catalyse projects. It's going to be huge. It represents a huge market going forward into the gigawatts. And if we look at Northern Virginia today, so that's the data centre capital of the world, there's about 2 gigawatts, or well, over 2 gigawatts, about 2.3 already today in Northern Virginia, and their power grid is struggling. They do not have enough power. Investment installed in new data because they can't serve it. However, nuclear and data are already working well together, and in that sort of power-constrained environment, nuclear is carrying 34% of the burden today, which is really good. Providing continuous, clean, green, secure energy for those data centres. But as we go forward and we look to see more projects, we need that brand new power source that does not exist. And there's the way these industries are meeting, data centres are getting bigger. So the state of the art currently is over 100 megawatts. There's advantages to being bigger, as with most things. And so they are tending to hundreds of megawatts, potentially in the future with one like very high, even into the gigawatts, which is a sort of sobering thought. Obviously, nuclear is tending in the other direction, and we're sort of at the point now where we're meeting in the middle. And those projects can be combined and create, a whole that works. So I don't need to lecture everyone on the energy density of nuclear, but the point I would like to make here is when we're talking about these large-scale projects, so this example is 100 megawatts. Now, if you've got a 100 megawatt data center, you're not going to struggle, albeit with today's connection dilemma, but you're not really going to struggle to get power to that site. If you're in the 500 megawatts, if you're in the gigawatts, and bear in mind these facilities tend to come in clusters for reasons of skills, for reasons of redundancy. Gigawatts and gigawatts of power is difficult to get into a place, let alone the constraints that we've got. So nuclear just rises to the top there as, quite frankly, the only viable solution for creating the new power to enable these projects to get through planning and to be successful. And so I think the message that we as an industry need to get across to the data center community, they're all scared, I would say, of nuclear. None of them want to own and operate a nuclear power plant. That's not their business model. They want to run data and come up with clever algorithms. So we need to show them how they can engage, and that ultimately through PPAs and long-term power purchase agreements. We can offer them something great. That's long-term price stability, carbon stability, because we can guarantee the carbon of that source. And quite frankly, that works whether you're a local user and you avoid the horrendous grid fees that we have in the UK, or as a distant user through PPA arrangements. All of those are possible. If it's new demand and you put it where you want, and the Venn diagram of good places to put data centers and good places to put nuclear reactors, they don't completely overlap, but they're not separate. There are some good synergies there. And so if you can co-locate, the benefit is enormous, assuming you have an enabling policy environment to allow that, which today you can't get the full benefits of that. But if you are a distant user, there are data centers here in London, not on the 100 megawatt scale, but certainly on the megawatt scales. You can still be an active player in a nuclear power project. You can still provide incredible long-term PPAs that will be part of stimulating those projects and enabling them to succeed. I've added on here, just in the concept of alternative use cases as the theme of the day. We're in a lot in the hydrogen space. We firmly believe nuclear has a huge role to play in the future of hydrogen production and the energy system that will feed. It's an interesting concept for the data industry at the minute. To achieve the 5.9 reliability, they use diesel generators as backup. They have huge diesel generators. They cycle them sort of once a month because they have to keep them ready, to keep them active. it represents the biggest sort of carbon source that they have as a business. So the Googles, the Metas, the Microsofts, they hate their diesel generators, but they can't get rid of them. Alternatives in the future, they're looking at things like fuel cells, which is great, but having fuel cells, hydrogen in a leaky vessel that sat around for 10 years and you never turn it on, it doesn't create our economic environment. If you can co-locate that with a wider hydrogen ecosystem that's producing the fuels and using that hydrogen readily, and the data center has a commercial mechanism around there to ensure it has enough hydrogen when it needs it, then that's a really economic way for them to decarbonise their full operations, not just their power. So really interesting synergies as we look into the wider nuclear use cases. And it's not just about nuclear feeding into data, so this presentation promised some synergies. The data industry and technology has a huge role to play as we transform the way nuclear is delivered. We know we can't do the same thing that we've been doing because it doesn't deliver on time, it doesn't deliver on budget. We need to do things differently, we need to bring manufacturing into the 21st century. Digital thread gets talked about a lot, digital twins, things like that. How you do that and how you ensure that your technology has got the right instrumentation, it's gathering the right data in the right place. Lots of that is nothing to do with the design, it's to do with how you contract your supply chain, how to get the pump data that the pump manufacturer wants because he sees the power in that data. There's a real art to creating that whole digital value chain across the entire life cycle of the plant. It's something we've been thinking about a lot, and working with the right technology partners to enable that. There's a huge opportunity here for that industry. So I chose not to try and embed a video in this presentation because it gave me headaches, but the storyboard on the top illustrates what I would have shown you, which is, and this is just one example, but you start with your design on the left, and you've got your design engineers, they're working, you've got a CAD model. We've now got to the point where people are wearing VR glasses and thinking about how they make this and keep out zones and all that sort of stuff, which is great. Digital technology has completely transformed the office environment from what it was 20, 30 years ago. It hasn't quite transformed the industrial environment. We're not quite there. We've made some valiant attempts, we've done some clever things. It's just not there. As we move into the final two slides, what we did, we had that CAD model of the module of the SMR reactor. Well, we went and built it, and then we flew a drone around it, and that drone took thousands and thousands of high-resolution images, stitched those together with an AI algorithm, and essentially recreated that CAD model. So you've got an as-built CAD model that you can compare to your perfectly, from the office CAD model, identify any differences. Really clever bit of kit, and that data then persists through life. That's a challenge in itself, and we need the right solutions, working with the technology providers. But being able to zoom in, you can see on the far right, you can zoom in to any point in that 3D model and get the 10, 20 photos that capture that from different angles. And so you can go and interrogate the condition of that equipment as it left the factory or as it was built into the reactor. It's really powerful stuff that is only the tip of the iceberg as we look to integrate some of these AI solutions that are coming down the pipeline. And our responsibility is to keep things open such that we can implement that, keeping the data in the right formats, ensuring that we've got the right sort of solutions for storing and maintaining that through life. And so just to sort of bring it to a close, personally I think nuclear and the data industries have a real close synergy together. It certainly seems to be paying dividends so far. It would be nice to get nuclear projects on the board and then really start to be able to offer those PPAs that can strengthen some of these relationships. But if we can provide a competitive price for into the far future, that's exactly what they're looking for. We'll take any questions there. Okay.
Thank you very much, Michael. So we're going to do the same format as before. So we'll invite speakers up in a moment to after Mike's presentation to get your questions lined up, basically. So we're now going to go back onto advanced modular reactors, and we have Mike here from UK Atomics who's going to present on that technology.
So thanks for inviting me here to talk. I'll jump straight into it. UK Atomics is really focused on trying to get energy back into the system in the same way that you drink a glass of water, the cost of that glass of water you don't think about, you just drink it. We should, in theory, be able to do that in the future with the cost of energy. So how can we reduce that cost? And this is the founding principle that our founders have got on our technology. So they want to have not just a low cost of energy, but they're trying really hard to get the lowest cost of energy. They're not looking for UK taxpayers to fund those projects. They're looking to find ways to ensure that you can invest in it yourself and develop the technologies and therefore develop the tech. They also want to try and think and consider about how do we stop that whole thought on nuclear and waste and how bad it is by changing the way in which we approach nuclear, i.e. the type of technology that we use. So our reactors will look at the waste and what's produced at the end. Instead of being hundreds of thousands of years, it's down to 300 years for the fission products that are left. So we can extract 10 times more energy from our reactor. We can do that because we're using a thorium fuel cycle with a molten salt reactor. Now, that thorium ball that you see there will produce enough energy for you for your entire life and everything that you use for it. And its cost is around about $100. There's loads of thorium in the world, and we will never run out of thorium, including the amount of iron ore that's probably available for wind and solar. So the levels of supply of thorium are by far in excess of what we need. If you look at nuclear as a whole, and you look at thorium as well, look at the size and scale. Now we're preaching to ourselves here because we're all probably mostly nuclear, but the amount of waste that gets produced in terms of the energy that you're using, power density. I think Mike, you showed it on your slide with the power density that was being used for the data centers. It's the same thing. We've got to look at technologies, and nuclear has that opportunity. It also, if you have the right kinds of technologies and you do allow that development, and don't get me wrong, development is needed, you can have opportunities for that technology to provide an incredibly low cost of energy to get a higher power density, even further than what we're thinking with conventional nuclear that we have in the current plants that are operating today. When you start to look at what that impact is, when you think about mining and the energy required to get the uranium, you can start to reduce the overall impact for net zero, the targets that we place. It's not just about the energy that we're producing and how we're producing it, it's also about all of the things that you're doing to create your products. So whether that be wind, solar or nuclear, the energy intensity that you need to produce that energy needs to be considered too. Our technology is a little bit different, as I said. We're looking at a thorium molten salt reactor and we use an onion core. Slightly different from what's been done before, but like all technologies, all SMRs and MRs, they were all developed in the 1960s, 50s, 60s. So really, all technologies are Gen 1, right? Well, not quite, because we're classified as Gen 4 reactor. We're looking at it from a slightly different concept of we have 40-foot ISO containers that can be transported on the back of a lorry. So things like our onion core can be held in this 40-foot ISO container, and you can ship your molten salt to wherever location you want, whether that be an industrial location that needs 100 megawatt thermal for its thing, or whether it needs 42 megawatt electric for its electricity supply, for its data center, its industrial application. You can choose and you can balance what you need. So in essence, we'd be able to provide electricity or process heat, or be able to produce things like hydrogen and how we can move that into ammonia to export globally. How we can support desalinisation, not really an issue for the UK, but if I go back to that beginning bit of energy equals prosperity, how do we produce clean water in the countries where they don't have the energy? What can we do? And that's where nuclear could provide an opportunity, but we have to develop technologies that can underpin and support that. So we're fueled by thorium with a scalable solution, and it's sustainable in terms of its model and how we're producing it. And of course, we're trying to get rid of all of that waste at a very low cost of energy. This is just an example of a 1 gigawatt electric facility, so it's 25 reactors with a few spare for locations if we want to have extra additional capacity on site. We also have buffer tanks that will store the energy. Each reactor is in a 40-foot ISO container, and on the back of it, you can just see on the right-hand side there, you've got the molten salt steam generators that can turn the energy into electricity, if that's what you want. Or you can have thermal heat supply. I'm just going to let you come up and do that. So, just whilst he's getting that, I'm about to show you a video that will just give you a little bit of. It's great seeing pictures, and that's all great and fancy, and wow, you can make a presentation. Well, I thought I'd rather show you a video and show you what we're doing, or what we have been doing over the last 9 years. So, if you can start that, and then.
As a nuclear fuel source holds the potential to change the energy sector and the lives of billions of people around the world. And today, it is 9 years ago that Copenhagen Atomics started the journey of realizing that potential. In this video, we'll take you through some of our main achievements this year, some of which you might have heard about, some of which you probably did not. And as a bonus, we'll show you some never-before-seen footage from the development of our thorium molten salt breeder reactor, the Copenhagen Atomics waste partner. From melting salt in the kitchen, building loops in a garage that sort of look like beer kegs, we've come a long way. And before we look at some of the progress, we want to say a big thank you to all of you watching and engaging in the content review. We love the comments, positive and negative, and we try to answer as many of you as we can. So, let's look at some of that progress. Our reactor simulations have been sped up and improved greatly. Many of them are now open source, which means you can run your own reactor simulations in OpenMC, and you can see how in our tutorial series. We manufactured more than 2,000 electronic control boards and sensors and have exceeded 2 million hours of testing across test platforms and components, including the first tests on our patented active magnetic bearings pump. And have collaborated with the University of Liverpool to conduct a peer-reviewed corrosion study of our purified salts, and have scaled our production capacity significantly to ton scale of FLiNac and lithium fluoride thorium tetrafluoride. We have sold 8 custom molten salt test loops, with 3 having already been shipped to universities, including MIT. But most importantly, we built the first 2 full-scale test platforms. Both are equipped with our patented Onion core, a completely new, very compact core design that uses heavy water as a moderator, optimizing fuel efficiency by capturing runaway neutrons in the lithium fluoride thorium tetrafluoride salt blanket. We're super proud of the milestones we've hit last year, and next year we're aiming to go even further. We've raised 25 million euro this year to keep developing the technology, and just brought on board a new CEO who will be taking charge of negotiations with governments in our next major investment round. Developing new technology and bringing it to market is a learning journey, and it takes time. But we'll show you it is possible. Stay tuned.
So I thought that would be good just to kind of show you and capture your kind of maybe attention to see what building the reactor is. And I think you said earlier, you know, X-Energy is looking to deploy. Well, we're all looking to deploy. I totally agree with that statement, and we're all doing it in slightly different ways. And there's nothing wrong with anyone's different way, different approach, and how they do it. But the key is, can you maintain? So I need to press another button on there. Can you maintain that delivery to the point that you can bring investor confidence to what you're doing? So the way in which that we do that is we follow a product-led approach to our development. We've got around about 70 employees in Copenhagen and a facility that's about 11,000 meters squared. We've actually just moved from our original facility, which was one side of Copenhagen to the other side, and this one is roughly sized to handle, if you were to put them side by side, maybe 100 reactors we could put in there. We're not looking to do that. It's a development centre, so it's actually only going to house 10 prototype reactors. So you've seen a couple of the things that are being done there, but the process that we follow is this design-led process. So rather than just doing paper designs and having to go through regulators and use data that's existing in the world that you can refer back to, because we're doing a molten salt reactor with a thorium cycle, we have to develop that data. We have to generate that information and make it available. So we have to kind of follow what the original process was to develop all of these technologies. This is what is done in every industry when you're developing tech, new tech. So we're just following what everyone else really does. But the approach for nuclear is it's quite different because people don't do that anymore. They can base it on previous designs, previous information, and then it comes to build projects and deliver those projects, and they have to justify those. So they still have, even with light water reactors, you'll still have to validate and verify with testing and development. So you still have this process where you need rapid iterations, but for that we need collaboration with industry. So we do collaborate. So we've got agreements with Topsoy on hydrogen development, we've got agreements with Alpha Laval on heat exchangers. We've got a bunch of collaborators that help to develop the tech. We have to start that process. So it ends up that we have a design that's on paper, looks like a nice model, a nice pretty picture, but actually we end up having to make the components on the side that you see there. The base testing for laboratory scale. The integrated effects test. Light water reactor integrated effects is basically water because you can simulate molten salt. But then you have to put that into a molten salt environment, so you have to test even further. You have to take that onion core that you saw the picture on, but we can't do it alone. We have to work in an open environment. And what we do is we deliberately do that. So things like reactor physics, we have our models that are open development on OpenMC. Things like electronics, we have components that we start to develop, and then we do the software integration and let the suppliers take responsibility for the long-term manufacturing so that they can do those products. We're not interested in manufacturing each individual component, but we have to at this stage to develop a supply chain. Same with pumping technology. You know, pumps didn't exist for molten salt, so we've had to develop the active magnetic pump that you saw on the screen. The salt that flows into that, we couldn't get it at the right purity level, so we had to remove the oxygen content, so we had to develop the salts. We had to develop the equipment that you can test the salts on and test the materials in. So we've had to develop static salt testing equipment so that we can understand what the impacts on corrosion would be, but by doing that you develop all of the joints, all of the flanges, all of the little pieces that people forget about when they develop the technology, so that you come out with the material test, not just understanding the material and how it will react in the environment, but also how it will work in a static condition or in a dynamic condition. And what we found is we can sell these components, this equipment, and people are buying it, and we get all the data from their testing. Hence why we've got so many test apps with data, because all of those people that we're collaborating with are feeding into central databases, because AI is becoming really important, and data centers, as you said, Mike, are really important. So the information is being housed and stored. And we use that to grow that technology fast and quickly. The next step is to move into our research reactors, our demonstrator reactors. So we've got prototypes. The next step is to turn those on criticality-wise, to get those into full-scale demonstrators. So they're already full-scale, but we've never turned them critical. We have to move that to a criticality state next. And then from that, we can increase the content inside and grow to 100 megawatt demo reactor, which is our commercial deployment. So you see some of those things that have been completed so far. Actually, this early 2023, filling that one, that's also completed. So we're then moving to a thorium salt version and then onto that criticality test. So that we can take our prototypes, our integrated effects tests, turn them into full-scale reactors for demonstrating and achieve all of those targets that we try to achieve with low cost of energy, future capability on waste burning, and effectively providing that energy as a service, which is what we're trying to do to support that long-term goal of providing green energy to a billion people. if you want to know a little bit more about us, please feel free to go to our website, have a look at some of the YouTube videos. There's a ton of them on there, and you can see real technology in real being developed by us in our factories, in our workshops, etc. Just a little bit different. Thanks.